Hello folks, today we are going to see constant acceleration. In many types of motion, the acceleration is either constant or approximately so. For example, you might accelerate a car at an approximately constant rate when a traffic light turns from red to green. Later, when you brake the car to a stop, the acceleration or deceleration in common language might also be approximately constant. So we can see we have a lot of things in your daily life and when we can to understand some acceleration as a constant acceleration. When the acceleration is constant, the average acceleration and instantaneous acceleration are equal, and we can write A equal average acceleration. We have V, final V, minus V0, VO, initial velocity, and divided by T, because the initial time is O, is 0. So you can to have this formula V equal VO plus AT when the A is constant. To find the position in constant acceleration, we have this formula. In a situation when we have an initial position xo, x0, and initial velocity v0 with a constant acceleration, the position x is. So we have here the time, initial velocity, and we can find the position. If we do some configurations here, we can put these two formulas together and put the time out of the formula, and we have this kind of formula. It's not our goal to show it here. You have a lot of people who show it in the internet. It's possible to find using these two formula, find this formula that don't depend of the time. Okay, now we will see sample problems. We are going to see the letter C because we are discussing about acceleration. We have another videos here, and we are discussing acceleration. The letter A and B, they are about average acceleration. Okay, let's go to C. A motorist is spinning along at 120 km per hour when he sees a squirrel in the road 200 meters in front of him. He tries to stop, but it takes 12 seconds for his car to stop. A. What is the acceleration of the car? Assume acceleration as constant. B. Does the squirrel survive? So we need to change kilometers per hour for meters per second. We have here a video about this method. Is called link chain conversion, and we have this video here. And we need to multiply by 1,000 meters divided by 1 kilometer, multiplied by 1 hour divided by 3,600 seconds. We will cut kilometers with kilometers, hour with hour, and we have meters per second. We have 33.3 meters per second. We will use it here. We have 0 final velocity, initial velocity 33.3 plus A multiplied by 12. We find A is interest a deceleration because it we have minus 2.7 meters for squared seconds. So let's go to see the distance here. If is more than 200 meters, unfortunately the squirrel is dead. If not, is less than 200, he will survive. Let's go to see. We have initial position O, 0 velocity, the initial velocity we have v0, we have 33.3, time 12 seconds, and we need to multiply. Now we will see that we have more than 200 and unfortunately not. Let's go to do some exercises. You can stop now and try to do the exercise. Okay, I will show how are the exercise. Okay, I will do this exercise. So I need to use here it because it's the formula when we haven't time, and we haven't time here, and we find a deceleration minus 128 meters for squared seconds. It's a very fast deceleration. Okay, here we need to put here the informations. We will not to isolate like this because we have squared t and t here, and we will see something like this. We need to put equal O, as in mathematics we need to find the x and xy. We use this formula, and we have t here, the same formula using x and t. We change to t, what is A, B, C, and we find t 7.5 seconds. Don't make sense. Minus 27.5 seconds, so it's 7.5 seconds.